Hi everyone, I'm glad to report our work dual bridging with adversarial noise generation for domain adaptive rPPG estimation. The rPPG technique can estimate pose-related metrics from facial videos and has a high potential for health monitoring. The latest deep rPPG methods can model in-distribution noise and estimate high-quality rPPG signals under intradata set evaluation protocols. However, deep rPPG models may not generalize well to the unseen noise and distortions. In this paper, to improve the generalization ability of rPPG models, we propose a dual bridging network to reduce the domain discrepancy by aligning intermediate domains and synthesizing the target noise in the source domain for better noise reduction. To comprehensively explore the target domain noise, we propose a novel adversarial noise generation in which the noise generator indirectly competes with the noise reducer. We also propose a hard noise pattern mining to encourage the generator to learn hard noise patterns contained in the target domain features. The proposed method is evaluated on 3 public datasets with different types of interferences under different protocols, and the results shows the effectiveness. So before we introduce the rPPG, we first talk about what is PPG. PPG is a traditional biomedical monitoring technique which can monitor cardiovascular activity by measuring the blood volume change. It usually requires a contact device, and the device can illuminate the skin with infrared or green LED light and then measure the color variation caused by the heartbeat. Based on the same principle, rPPG technique can measure the heartbeat signals under ambient light in a non-contact way using normal RGB cameras such as the web camera and also the industrial camera. The rPPG has multiple downstream applications, such as the clinical monitoring in ICU, NICU, and also during the MRI scan. It can also be used to do the sleep monitoring, physical training, emotion analysis, face anti-spoofing, and etc. Consequently, in real applications, it will face various scenarios such as different types of device, different kinds of lighting condition, facial expression, and also other interferences such as the video compression, skin tone, and head motions. Existing methods tend to boost the generalization ability of rPPG in a noise modeling perspective. It is usually a GAN-based framework. For example, here, a discriminator is employed to distinguish the generated feature from the original one, and this method can perform well under the intradata set evaluation protocols since the in-distribution noise patterns are thoroughly investigated with a large number of adversarial learning iterations. And however, they may not aim to handle the unseen scenarios. So an intuitive solution is to adopt the unsupervised domain adaptation technique to bridge the gap between the source and target domain, and it has multiple success experience in the natural imaging tasks. However, the domain classification may not give sufficient information in rPPG regression task. Therefore, in this work, we propose a dual bridging with adversarial noise generation to boost the generalization ability of rPPG. First, let's introduce the basic configuration of rPPG estimation. Given an input phase video, we extract the spatial temporal map by calculating the mean RGB values of the local facial ROIs. Then the SD map is taken as the input of the feature extractor to obtain the intermediate feature. Here it is the source feature in the source domain. And finally, we got the rPPG signals from the higher layer rPPG estimator. The PPG measured by the contact device is taken as the ground truth to supervise the network learning. For the target domain, we go through the same process, but without the supervision of the ground truth PPG. We want to have a noise reducer, NR, to denoise the intermediate target feature. So the first bridging is the adaptive noise reduction bridging, achieved by the discriminator that tries its best to tell which domain the feature is from. And here we update the noise reducer with a classification loss. However, the domain classification may not give sufficient information for rPPG regression task. Considering that the ground truth PPG only exists in the source domain, we want to transfer the target domain noise into the source domain, which forms the synthetic feature here, and then use the ground truth PPG to further enhance the noise reduction ability. And this is the second bridge called the complex noise bridging. To achieve this, we built an adversarial noise generation module which adaptively generates hard noise conditioned on the current noise reduction module during the training process. So in the second bridging, the domain classification loss aims to train a better generator G and the rPPG regression tasks help further revise the noise reducer module. On top of that, we also introduce a hard noise pattern mining module, which filter out the denoised feature slots and keep the hard noise features to further boost the dual bridging process. We evaluate the proposed method on 4 datasets: pure, SCHR, UBFC, and cophase, which including variations such as the illumination, facial motion, expression, camera and video compression, skin tone, and also heartbeat ranges. We evaluate task-independent scenarios on SCHR datasets, which involves different activities. Each activity is regarded as a task here, so the unseen interferences are mainly introduced by different types of head motion and facial expression changes. We set one task as a target domain and the other task as the source domain. From the table 1, we can see that we achieve the best performance compared with the state-of-the-art. On the UBFC datasets, we evaluate under the participant-independent protocol, where the subjects used for training and testing are different. Compared to the generic UDA methods, our proposed method can provide more detailed information for noise reduction supervision and achieve better results in general. We conduct cross-dataset evaluations between pure SCHR and UBFC, where the domain discrepancy are much larger. We beat the state-of-the-art in most settings and metrics. We also conduct the ablation study under the cross-dataset setting between SCHR and pure datasets. The results and visualization of the estimated rPPG signals verified the effectiveness of each modules and the strategies we proposed. For more details, please come to our poster on Wednesday AM 203. Thank you.